How's everyone doing? That's a lot of big thumbs. Yeah. Yeah. Okay. Double? That's good. Good, good, good. How'd that homework go? Yeah. Okay. We'll try and address some of it. I saw a pretty common misconception about like the humps in the spectra. Did that confuse people? No? Everyone got it. I should just not even discuss it. You want to discuss it? Oh, okay. Anyone else need that homework? It's gotta be here, I guess. What's this? What? No, it's not Hurricane Milton. It is a hurricane, but it's not Milton. Satellite? It's just a hurricane. It's not Milton. No, 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 no. This is I think it was last year or 2021. I don't remember what the name was. Um, big hurricane. We always get hurricanes. If you couldn't see like the states, US states, any way to tell that this hurricane is near the US? The direction it spins. Okay, so has anyone been to like South America? Okay. Has anyone been to Australia? Has anyone been south of the equator? Oh, okay. Okay, south of the equator. Yeah, so some people say that when you go south of the equator and you use the restroom, the toilet goes the opposite direction. Is that true? It's just the way the water comes out. That's correct. So you have to know a little bit about toilets, and maybe that's not something you learn in class, but you're learning it here. So we will find out today why hurricanes rotate in the way that they do. We'll finish up with the discussion of light, and we'll talk about just really briefly why the sky is blue. And then we'll talk about, for example, you've heard this, everyone's really upset about the fact that maybe we're producing a little bit too much CO2, and that's dangerous. We'll talk about how that happens in terms of the physics, okay? Not the economics. So, okay, turn that on. You saw this in your homework? And you're like, oh, I got it right away. But just for everyone else in the class, can you explain that? So there are two humps in the spectrum. Let's remember that the word spectrum means a range, right, of something. In this case, we're talking about a range of light. So on the left-hand side, we're talking about ultraviolet, very high energy. Down here, we're talking about the infrared, low energy. It's important to remember that while our eyes can tell the difference between these colors here, blue, green, red, right? There's a spectrum of colors that live in here. But our eyes fail after that. They can't tell the difference between any of the different types of infrared. But there are different types of infrared. So infrared that's out here has less energy than infrared that's here. And it has less energy than here, right? Energy is increasing as I go towards the blue. And if the figure kept going, this would be like X-rays and gamma rays out here, right? Okay. So I asked you to do two things. I asked you to draw something that was blue, and I asked you to make the thing hotter. Now we've said that if something is shining blue, that it has more energy than something that's shining red. But does that mean that these two objects have different temperatures? Raise your hand for yes. Raise your hand for no. Raise your hand for I don't like raising my hand. Still good. Okay, that's less than normal. Okay, so because they are not shining, because they are reflecting, then it doesn't apply here. We're thinking about two different concepts. The color of something doesn't tell you about its internal temperature. Because if I turn the sun off, all of this light disappears. Right? This is only possible because of the sun. The sun puts out white light, and there is some absorption of red, but a lot of absorption of blue. So the thing appears red. As opposed to the thing is hot, so it's emitting light in the infrared. These are two different peaks. This is energy from the sun in, bouncing off, and coming back. This is the light that you get without an illuminating source. Right? Which of these two is applicable to me? This one, right? This is what the snakes see. I emit in the infrared. I do not emit in the visible. Right? Dr. Manhattan emits in the visible. Do you know who that is? Yes. Okay, that's also homework if you want. You can watch that. Good physics. Okay. Yeah. Okay, that's as long as I want to spend on it. But if you have questions, you can send me a message. You can come to office hours. We can talk about it more. Okay. All right, we're ready. Let's go. Brains. Did I hear groaning? Okay. Let's remember things that we said in the past because we don't delete stuff in this class as soon as we hear it. Okay, based on the figure. Now this figure, let me explain it to you and then I'll read the question. Here I'm showing altitude. So this is up at the top of the atmosphere. This is the surface. And this is temperature. So this is Venus, very warm. And this is the Earth. And this is Mars. That's kind of how you expect, right? We said that the surface of Venus is quite warm. So that's over here. And then it gets cooler as I go up. You'll recognize on Earth, I have this little peak in the middle. What's that caused by? What's that? Ozone, right? And what's ozone absorbing? UV, right? So this is protecting us from really good suntans, right? Really, really looking great, okay? And so my question is, we expect convection on the Earth down here, right? And we said in a different clicker question that it might occur elsewhere. So now I have a question. We have Mars here. Do we expect convection in the troposphere? That is to say, from here down. Do we expect it to be more, less, or as active as the Earth? Can you write it? Oh, I tricked like nobody. Is that it? Everyone done who wanted to click in? If you forgot your clicker, you can write them down and hand them to me at the end. Okay. Almost everyone said less. Why would that be? Yeah. Because what? Sure, but what does that have to do with this? Yeah. Because what's colder? Yeah, so this part here is colder, right? So basically the idea was, how does convection happen again? What are the conditions? Yeah. Yeah, you got to heat at the bottom and be cold at the top, right? Because if you're hot at the top, that's like how nature wants to have it, right? Because usually fluids, they expand when they're warm, and so then they rise. So hot air balloon, you heat up totally normal air, but it's hot, so then it goes up, right? Okay, so because it's cooler, we expect less vigorous convection. Okay. Fair? Cool. Okay, I said, and I'll say like probably 6 more times, if you can remember this, right, that the most energetic, I'll figure it out someday. I need like a red pen. It's this one. If you can remember this, you can remember the structure of the atmosphere. So at the very top, we talked about the fact that X-rays break apart the atoms at the very top of our atmosphere. And then the ultraviolet gets absorbed by ozone, right? This heats up the atmosphere. Visible has no problem, goes right down through, except for blue does some wonky stuff. Right? And then infrared is really, really in trouble because the infrared likes to interact with water vapor, and water vapor is really abundant. So if you had a cell phone and you were trying to make a phone call, but if you used infrared light, you'd have a couple issues. What would the issues be? Let's say I have an infrared cell phone. Oh my God, tremendous. Yeah, one would be very hot, which would be unfortunate. You're like talking, and then it's like heating up your ear. Probably not good for your ear. Yeah, it wouldn't work very well inside buildings. Wouldn't work well inside buildings, right? Infrared light doesn't go through building walls very well. That's why we have insulation. That's great. Third one. Let's say I'm out in a field, right? And it's like there's a lot of moisture, like today. You couldn't make a phone call very far because all of the waves would get absorbed by the water in the air, right? Okay, so that's why you can't see it on here, but way down below with less energy, all of your Wi-Fi, Bluetooth, all of that is through radio waves. Okay. Okay. So now we fully understand this, right? Everyone's an expert? Okay. I'm going to teach you about one more layer. This one, we're not going to spend a ton of time on. This is the layer above. If I go up above 500 kilometers outside of the atmosphere, we call it the magnetosphere. And this is this giant envelope that goes around the entire planet. It's made of the Earth's magnetic field, and it can protect us from harmful radiation from the sun in the form of very fast electrons and protons. So we're down here, that's us right there. And then electrons aren't just like smashing into our head. Great. But what they will do instead is this acts like a giant catcher, what are they called? What? A net, yeah, there you go. So this acts like a giant net, but what it does is it funnels all those particles onto the head of the planet. And so particles from the Earth, from the sun, head towards the Earth, they get deflected, and then they go down along the magnetic poles. And they hit the north and the south of the planet. And you get this. That's a real photo. That is the aurora borealis, the northern lights. And the colors here are due to the fact that, we were talking about these specific transitions that can happen in atoms. So actually, we can figure out what atoms these are in the atmosphere that are interacting with those particles in order to make this light. So the red here and the green, normally you see aurora looks really green, and sometimes you see red aurora above it. Sometimes it's purple. Depending on where you see these different colors, they represent different species. Usually, green here is the interaction of particles with oxygen, O2. And if it's low, that can be nitrogen, if it's red. And if the red is high, that's usually single oxygens as opposed to O2 together. I think I have one more example. Yeah. That's pretty sick, right? So these structures, they look like sheets or like, yeah, sheets, right? Like a piece of paper like this. That's because this is the magnetic field of the Earth coming out of the Earth. So in order to have aurora, you need a magnetic field. And then it comes out of the Earth like this, and particles travel down it and smash into the atmosphere exactly where it is. Now these photos don't do it justice. Maybe I'll find a video that's really cool. Did we show that in this class already? Where they flap. And they flap really fast, like weirdly fast. So I saw them in Iceland, and you look up, and you're like, is that a cloud? No, it's like moving like this, right? So it goes like this, right? They're like ribbons flapping in the wind. And so these things look stationary here, but all these particles are moving back and forth through the atmosphere.
Like a flag?
Like a flag, yeah. But like many of them. So you can imagine there are many field lines that are coming out like this. Oh God, that's not very good. Okay, like that. And so they'll be stacked one next to each other in rows, for example. And then particles will come screaming down, smashing into the atmosphere. Okay. Nitrogen, oxygen, and you see how they're kind of stacked on top of each other? That's different particles with different energies smashing into different parts of the atmosphere. Okay. Just pretty, you know? I don't know what to say about it. It's gorgeous. You won't have to memorize the behavior of these. I may ask you a question like, what things do you need to see aurora? For example, what type of things that I just talked about are necessary? Like a magnetic field, right? You need an atmosphere, and you need those two things to interact. Jupiter has a huge magnetic field, and it's chock-a-block with atmosphere. So probably has some sick auroras, right? It does. But I'm getting ahead of myself. Okay. So I promised you lecture tutorials. Let's see how well we understand this idea of light getting down to the surface. Okay, you are all going to work for NASA today. I need you to either approve or deny some grant proposals. People have been asking me for hundreds of millions of dollars to put telescopes into space. And if you do it wrong, you're wasting the taxpayer money, which is your money. Okay? That's fake, by the way. Not related. Okay. So take one between two people. Five. You guys working together? Oh shit. Anyone missing one?
Yes.
So we'll do it right reading.
I have. Finally getting into all weather.
I know, right? Except for when I teach, then I get warm. Beats the purpose.
Like, should I have some jackets, but not have any?
Yeah, right.
This is the most. Oh, that's why.
Yeah.
Yeah, sorry. Folks, to clarify, the color here, just think that this is blue. Right? A little bit of atmosphere at the top, lots of atmosphere at the bottom. This is a mountain. These are trees. That's all. Oh, that might still be in there. You're gonna see wrong. Oh, I just updated everything, just want that folks to know. Like, if you don't get it by Thursday. Yeah. So five things on that one, didn't we? Turn it, try to resolve it together. But I still think one of the things that's homework and people struggled on, I turn it into. Right. So it's hard to.
My partner said we're gonna pass it. And we both feel the same shape. Maybe I didn't, maybe by name.
What is your name again?
Eric Gillespie.
I need like a notepad to check. Oh, all right. Got you.
Thanks. I also had a question about the check-in. So for the next check-in, when we write down feedback for every single words or
So there'll be but it'll just be an update on the one part. No need to read it. All right.
I can suck them pretty much down. But it's the reason. Oh, did I never think about it. I feel like I was eating.
The largest building in the States.
It's a.
You done?
No. We're going back to the previous room. Is that okay? Right. Hold that one. Okay. Do I work in with the? Yeah. Okay. Does generate yes to the side. Okay, so let's say I think we generate power. No reason to keep going. Before we make you guys all the back.
Same way that's. You have $5 you have to give it to you're the downside. Like Anne-Marie, take it to the atmosphere. Yeah. No. So if you added Anne-Marie on the same. Not for it.
Robert is like, I really have one. Why would we not? No, we already have it. I'm not sure. You already have it. Well, I could have
Really good.
I think that.
Look at the yields. Yeah, I don't think it's a nobody. You know, it's just quite funny. But they don't get very rarely get. One of my friends looked at the phone, another one. Thank you. That's what ours. That's usually How many people are on the last page? How many people are done? Oh, wow. All right. Calm down. All right. We're gonna do, so we'll do another one on Monday, on Tuesday. We'll do, whatever the count. I switched them today.
What's next?
Greenhouse.
Greenhouse. Okay. Greenhouse. That goes into.
No, so, yeah, so we'll do global warming a little bit. Things like, we won't have a separate lecture tutorial. We'll go into.
Oh, did you find everything?
Yeah, at the bottom, you should say which one is the one you find this. They'll, really.
Yeah. Satellite. These actual products, like any projects.
Not even.
I know there's a bunch of really tall stuff.
Yeah. Well, I mean, so they're all based on real things,
I'm saying.
but no one would propose like a gamma ray telescope on the surface. Yeah.
I mean, that's what I was thinking.
Yeah, we have telescopes of every type. Just fine. Bouncing off the atmosphere. They bounce off a layer in the atmosphere. That's why people are. Well, actually, can't get signal on an airplane because they think about the way that works. You know, the windows are where the radio wave can get out easily. But so now your signals are going out this way, and they need to self where the self. So you know, depending on the flight, it's usually about 1,000, 2,000. I don't recommend Okay, how are we doing? We close? This way? Raise your hand if you're done. Oh, all right. All right, why don't you bring them down if you're done? And that way I'll kind of get a sense. Thank you. Thanks. Oh, wait. In is here. Out is there. I need like signs. How do you go? Yeah. Okay. So if you're not quite done, I apologize. A little pause. And we'll continue. Okay. Different wavelengths of light affect the atmosphere in different ways. So one thing that we're going to talk about first is why is the sky blue? It's just one slide. I know it's going to be really exciting. Maybe not that exciting. And then we'll talk about the difference between weather and climate. So weather is what you experience on a day-to-day basis. Climate is what you experience on the time scale of years, tens of years, to hundreds of thousands of years. Climate is not whether or not it was windy today. It was, is the Earth hotter than it has been, right? Okay. You know, when you think about something like Venus, that's just about the same size as the Earth, and you wonder what went so wrong, that there is no oceans, no life that we can see. You want to understand the climate of Venus. You don't particularly care about the weather. That make sense? Okay. Here's why the sky is blue. We were talking about the fact that visible light basically unimpeded. So here's me on Hawaii time, on vacation, having a great, vacation, not doing any work. And I look up at the sun directly overhead. And what does the sky look like? Well, white sun and blue sky. What's really happening? Almost all of the light is coming down, and I get a lot of blue and red together. I didn't add the full rainbow, I'm sorry. We're just going to talk about the difference of the two colors here. But the atmosphere is kind of good at scattering the blue light. So sometimes light would hit an atom and then bounce off, but then one from over here will scatter back into my line of sight. And the way that I see that is, even though it's all light from the sun, it appears like blue light is coming from all of these locations away from the sun. So they're all bouncing from away from the sun into my eye. So I interpret that as light is blue in that part of the sky. Does that make sense? So it's not reflection off of the ocean back up to the sky and into my eye. It's just scattering. Okay? It's not absorption. The atmosphere absorbs a very, very tiny bit of light, but mostly it's absorbing the infrared light after it goes to the surface. Okay, and then I'm going to FaceTime my brother. He lives in Tampa. So he's over here, and he's finished with work, and he's like, oh, it's a beautiful sunset. Okay, so we're experiencing the same light, but the light that he's experiencing has gone through more of the atmosphere. What do I mean by that? So if you imagine the Earth round like that, if I go straight down, the atmosphere pierces just the very tiniest bit. Whereas if I go from the side, there's a longer path for it to travel, right? See how over here, this is a short distance compared to this, which is a much longer distance. And along that path, blue light has more opportunities to scatter. So the blue light here goes and hits someone in Mexico. And the blue light here goes and hits someone in, New Orleans, right? So the blue light gets scattered out of the things that he can see, and all that he sees is red. He sees what's left over. Does that make sense? You've also seen this. If you've ever gone up to a hillside and you look out across the city and all of the lights look yellow, you ever wondered why that is? Are those city lights yellow?
Yeah.
No, because when you go and you stand under a city light, it's white. So something weird happened, right? You're on a plane, you're landing, every single one of the lights is yellow. That's not a coincidence, right? NASA must have done that. Okay, so the reason for it is because they're scattering the blue light. So that lamp that normally is white loses all of the blue. And the only thing that makes it to your eye is the red. Now, it's not so bad as the sunset, right? Because obviously that travels longer. But you get kind of an orangey color. Does that make sense? Could you explain this to someone else? No. Okay. Where do you want to go? Where do you want to start? What part doesn't make sense? Why? Okay.
I'll get it.
That's fine. That's fine. See if there's another way to say it. Yeah, I mean, the way that I think you can think about this is like we were looking at a prism, right? And basically the atmosphere is acting like a prism, but this is a weird prism where it doesn't split all the light into a rainbow. it just kind of splits blue out of the way. So you can imagine here it's going straight and it's just kind of getting diverted to all of these places first. And then what you're left with is red. So when I'm standing here, like it's like all the blue gets splayed out or like tilted out. And so then I look around the sun and it looks blue. Another way of thinking about this is what would it look like to be on the moon where there's no atmosphere? What color is the sky on the moon? Black. If you don't have an atmosphere, you'll just see a big bright sun and the rest of the sky will be black. And as long as you're not staring at the sun, you'll see stars. Yeah.
Blue light scatters because of what our atmosphere is made of.
Kind of.
So like a planet, so there's a planet similar to Earth that had an atmosphere made of different things. The daylight and
It's a little tricky because the way that it works is the molecule itself is not like, oh, blue is preferential. It's something called Rayleigh scattering, and it kind of just affects all wavelengths, but it affects blue wavelengths more. So with a different species, let's say a CO2 atmosphere, you don't have a blue atmosphere in the same way, but you still have sunsets in the same way. Does that make sense? Okay, here's what I'll do for Tuesday's class. I'll show you a sunset on Mars. They happen, obviously. And we have spacecraft on the ground with cameras and they take pictures. Okay, what was I saying? Oh yeah, on the moon, no atmosphere. You have basically a spotlight, right? Right now, it's really easy to see in this room because there's a number of different lights and they're all spread out. They're not super bright. Now imagine how weird it would be to stand on the moon, just one giant spotlight and nothing to smear it out, right? What the atmosphere is essentially doing is it's like taking a giant translucent object and letting the blue light shine into it so that you smear out all that light across the entire planet. So it could just smack dab above you, right? Is that helpful or worse? Okay. You could have said worse, that would have been fine. All right, let's talk a little bit about weather. And this is just going to be a short thing talking about the rotation rate that we were talking about. So this is Hurricane Katia, Hurricane Irma, and Hurricane Jose. And of course, they name them not after people. These are K, I, J. And so this is in the order in which they appear. So I comes first, J comes second, K comes third. And as tropical depressions, which are small storms, grow and turn into hurricanes, then they get classified. And for something like Hurricane Katrina, which is so damaging, they'll take that K and they'll never assign another hurricane that name, right? We'll just use a different K. So if you wait long enough, hopefully you get a Hurricane Mateo and everyone gets seriously. Okay. And the same thing that you see here, that they're all spinning, right? They're all spinning. They're also massive. Yeah.
Is there like the naming, like the lettering of it, is that every year? How do we know when?
Yeah, so at the beginning of the year, we start with A. Yeah, sorry. But not necessarily like Adam.
Yeah.
Yeah, just A and a name. Okay. These are massive. But it's a little hard to see here, but that is all of Florida. That's all of Cuba. And Irma is like the size of Cuba.
Two questions. One, was Milton big enough to keep its name?
Oh, probably.
And then so the next one would be Henry.
What?
Next hurricane would be Henry.
Yes, and I believe there is one right now. Yeah, it's something like that. So there's this great, I showed you zoom.earth, right? And it'll show you both the newest hurricane and its path. And they use two different models. There's a European model and an American model where they try to predict where they go, because obviously knowing where they touch down is really important. We talked about Hurricane Milton. Some folks heard about the fact that this is one of the largest hurricanes possible, mathematically possible. And that is only slightly true. So it's within the top 5 of anything that we've ever recorded. But when we say mathematically possible, That means for the current sea surface temperatures. So as the sea surface rises, in temperature, not physically rises, as it gets warmer, then it has more energy to draw. And so hurricanes can and will get strong. So in 50 years, will every hurricane look like Milton? Possible. Right? That's yeah. So that's why I don't buy property in Florida. My brother did. I don't know. Oh. Yeah, it could be eroded. Yeah. And with sea level rise, you can go into the databases to like calculate how many feet it rises. We could do a whole class on how fucked the Earth's gonna be, but I don't think it's gonna feel good. Yeah. And even though it tells us about our place here, there's a lot of good signs, right? The awareness that especially this generation has about the current issues is better than it's ever been. The transition to solar, the transition to renewable energies is growing at an accelerating rate. So it is bad, but honestly, I think if you don't scream about how bad it is, no one will take it seriously. But I would never underestimate human ingenuity, right? Especially when it comes to the destruction of people.
I swear I'm not vegan. It's like the cow farms and all that stuff, like the factories and stuff like that.
No, so about 100 companies produce something like 60 to 80% of all emissions. Yep. And in particular, they want to point fingers at you. They want you to be responsible for your global footprint. They want you to be responsible for what you eat. They want you to be responsible for how much you travel without ever taking into consideration lowering their emissions, right? Because then if they can make you argue with your nearest neighbor, it's much easier than looking at them and asking for quotas or caps on global emissions. Yeah.
One thing I always found funny about them always like blaming like animals and stuff was like I saw a really cool like very interesting counterpoint of somebody like, okay, you stay in a garage with a running car and I'll stay in a garage with a cow and see what happens then.
Yeah, I mean, so let's be clear. They're both dangerous, right? They're both dangerous for extremely different reasons. We'll talk about greenhouse gases in particular. The most dangerous greenhouse gas is water vapor, right? It's just that we can measure very accurately the abundance of CO2 because that is not naturally produced. Farts are naturally produced. That is just as dangerous in a lot of contexts, right? So for example, people who are like, well, you should be eating crickets. There's actually a lot of science that says you should be eating crickets over red meat. Now, will that fix the problem? No. Because capitalists going to capital, right? Okay. Hold on, I can't go on too many tirades. We're gonna do this, guys. Okay, so let's figure out what's going on here. So you have these giant storms. Why are they rotating? They're rotating because of Earth's rotation. Okay. Why? So hot and cold air is correct in terms of a tornado, but tornadoes don't get this big. Nope. Okay, so this is a really weird thing, right? Okay, we want to understand why hurricanes curl. We want to understand, are the winds at Venus strong? Why or why not? Does the atmosphere respond to the planet spinning? I said this before. I said something about rotation rate. And you're all like, okay, I guess he's the professor. Right? No one even said, I said that at Venus, the winds were strong or not strong. What is Venus's rotation like? How long is its day? Yeah, it's like a year, right? Its day is longer than its year. And I told you that the winds on the surface are basically nothing. Okay, we're going to understand why that is now. We're going to understand why a faster spinning planet creates more violent storms and powerful winds. Because the atmosphere itself is going to respond to the fact that the Earth is rotating. where the planet is rotating.
Doesn't the rising ocean temperature affect like the size of the hurricane, its impact?
That does in the context of the fact that it's warm. More available energy means that you can make more powerful storms. So essentially, and we can talk about how hurricanes, if people want on hurricanes, like at the beginning of Tuesday, how hurricanes work. Okay, like 6 people. All right, that's enough. All right, we'll do like 3 minutes on how hurricanes are formed. You have to yeah. Hurricane, okay, tropical storm. Yeah. Yeah, we'll talk about that. We can talk about that. No, I mean, if you want, we can spend, a good half, because this is really interesting stuff, right? How does planetary climate work? Why do they rotate like this? Why do we get them only on this side of the country? Like, did they do something bad? Right? Like, I mean, my brother lived there, so okay. All right. So let me, has anyone, has anyone ever been to a playground? Recently?
Yes.
Okay, good. Have you ever been on a merry-go-round? Like the one that you spin with your friends? No? Raise your hand no. Okay, you're gonna watch a video, and I know, it's super exciting. And we're gonna look at something called the Coriolis effect. And this is how your perception changes when the object that you're on is rotating. So if, for example, I were to throw a ball at my friend on a merry-go-round, is it easy to do? No. And if I like kick my friend, don't do this, but if you did, if you kick your friend, which direction do they go? Okay, let's imagine, I'm not gonna do it here. This is spinning around like this. Can everyone see this chair? Okay, it's spinning around. If I kick my friend from the center outward, does he go outward? I assume no, I've never kicked my friend. How can you be so violent? What's that?
Then it depends how fast you spin it.
Oh, wouldn't it depend on how fast you spin it? That's a very good question. Because if I wasn't spinning very fast at all, then yes, that would be right. I would kick him and they'd go out. If I was spinning very fast and they kicked them, right? Which direction would they go? Yeah, kind of in the direction of the spin, but out. Because at one point we talked about the fact that objects in motion remain in the motion unless acted upon by something else. Now, in this case, the kick is certainly an action, right? But I still have all of the speed from going around in a circle. And now I've just added a little bit more. So now I'm adding both of those together, and I'm going to get the person I kick to move, right? This is my claim. So let's see if it's true.
Would it depend on the force of the kick? Say it's
Yeah. And proportional, of course, to like how fast you're moving. So if you kick them really hard, it doesn't matter how fast you're spinning, right? Yeah, good. Okay. And this is a very prestigious, Oh, you better work. Let's go.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion. Here's the game, right? You're going to throw the ball straight to, what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah.
Right, what's going to happen, dude?
I was going to veer off to the left.
So the ball is going to swerve off to the left.
Yep.
And you might catch it.
Possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, so everyone, no, hang on, one more.
He's
not
arrogant.
Just quietly
He's
confident.
not catching it. He's not
Really?
catching it. No.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying comes to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up?
All right, where will it end up? Hold on. We're going to ask this with a clicker, okay? Oh, come on. Don't, Monty. I hate this. All right. So here's how it's going to work. If it's to the right, okay, if the ball's going to go to the right, it's A. If the ball's going to go straight, it's B. If the ball is going to go to the left, it's C. If the ball is going to come back to the person, it's D. Let me show you the setup again. Oh, God. You think I can tell colors? Okay, so they are rotating this way, and she's throwing the ball across. Okay, let's try this again. A, B, C, D. I guess I should have like put little things on it, right? Okay, click in. I know I interrupt your TV time, but oh my God. Okay, ball's going this way. A. Okay. A. B. C. D. What was your name again? We got it?
Yeah.
Everyone got it? Wow. Okay. Interesting.
Oh,
Cool. Okay. Where'd he go? Yeah.
You might.
He's not arrogant.
And you think it goes straight ahead, but you think you'll be the one catching it. Yeah. Be caught by the person opposite. Will it be caught by the person to the thrower's left or by the person to the thrower's right?
It's a good thing we didn't do that, right?
Or by the person to the thrower's right. Right, in your own time, throw the ball.
I got this.
Oh. No, the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw? Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, I did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
Nope.
No idea. It's called the
Okay. Do you know why it did that? Why did it curve to the right? Yeah. So from their reference frame, right, from where they're sitting as they're moving, the place that they're moving relative to the original path of the ball is changing. The ball did not turn left or right if you're standing on the grass. The ball went straight. They moved as the ball went straight. The same thing is happening when we think about a storm. Okay, let's say wind is moving along the equator. Okay, let's say you have wind blowing from east to west, but the Earth is rotating. Okay, as the Earth rotates, wind is going to turn because of the rotation of the Earth. The fact that the Earth is moving underneath something that is flying above it. Let me show you. Okay. And then, yeah.
Kind of similar how they found out that these things.
Yes. Yeah, so that, remember we were talking about this pendulum that you can use in order to show that the Earth is rotating, right? That is exactly the same phenomenon that's happening here, except with the Coriolis force, we tend to think about it in terms of something like a projectile, right? Or something like wind or water. So for example, if you were shooting a weapon very far away, you have to account for the fact that when you shoot, say, the cannon or a rocket, that the Earth will have rotated. So in the perspective of where you're shooting, you want to hit, let's say I want to hit James, right? I don't aim at James. I aim opposite one of these two directions so that I can have it curve and hit him. Yeah, so there's a lot of studies done when they created cannons, like why are we missing, right? So there's all this research that goes into how do you fire artillery effectively, right? And you have to account for where you are, which direction you're shooting with respect to how the Earth is rotating. This effect is more intense if you're rotating fast, right? If you're rotating really quickly, and imagine the same example where I'm trying to hit a student, right? If the student moves to the left quite rapidly, then I have to aim quite far away to compensate, right? If the planet is not rotating very quickly, then I can just shoot straight. And sure enough, when I'm in the northern hemisphere, air is going to curve to the right, has that signature curl. Right at the equator, the effect basically goes to 0. And in the southern hemisphere, it curls to the left. So in the southern hemisphere, they're called cyclones. They're not different from hurricanes. They basically only exist in the regions that are sort of north of Australia, Indonesia, into like the bottom of the Indian Ocean. No hurricane or cyclone can cross the equator. So as a storm might be headed towards the equator, the Earth's rotation is pushing it, literally pushing it up as it rotates away. And so I can show you in the beginning of Tuesday's class, we'll talk about the dynamics, and I'll also show you the paths of all hurricanes that we've ever reported. And it's amazing. It's just through the center, it's just an empty line. You want to be like totally free from hurricanes? You live in Ecuador. Okay, questions about this? Yeah.
What are monsoons then? Or where are monsoons?
Monsoons are actually just, they're not cycling storms. They're just dropping lots of water.
Oh.
Yeah. Typhoons is the hurricane equivalent, but that is for the western part of the Pacific Ocean, the eastern part of the Asian continent. Does that make sense?
Like Japan and.
They call them typhoons. What?
Typhoons,
Yeah.
it was hot the whole week we were there, and then one morning we woke up and then it was just a typhoon out of nowhere.
Typhoon or monsoon?
No, they said it was a typhoon.
Okay,
Because
okay.
it was coming and going, because the week after we left, the whole week they had a storm, a typhoon storm.
Yeah.
But they're scary, like, you don't think you see a storm that bad until you see it, and you're just like, it delayed all of our plans for the whole day. I was like, wow.
Yeah.
Just had it.
And on travel, that's a lot less fun. You're like, I'm literally wasting time. Okay. Yeah, so let's do a little thing at the beginning of Tuesday's class. We'll talk about how storms form. Okay. Hold on. Don't run away. Okay. So we haven't talked about it yet. We're about to talk about this idea of greenhouse gases. So I just want to summarize a few of the things in terms of the planetary processes we talked about so far. So in the absence of greenhouse gases, a planet's surface temperature depends on the size? No. Right? What does it depend on? Yeah, what does the surface temperature depend on?
How close it is to the sun.
How close it is to the sun, right? Come on now. Yes, right? What else? Oh, God. Why is this not working? Okay. Rotation rate? That's a weird one, right? What does the rotation rate do? Yeah, like it says like where is the light going, right? So if, for example, you only ever showed the same face to the sun, you'd have one side that was really hot and one side that was really cold, right? And maybe humanity would only live on this like ring right at the edge, right? And if you rotate the planet, you kind of like smear out the hot and the cold. And if you have a faster day, then the day-night cycle is less intense, right? So you can imagine if we got a full day every hour, then you would basically have constantly the same temperature. As opposed to now, you wake up, you need to put on a sweater, and then you come to class and you need to take the sweater off because it's been all hot all day. Then you go home, you need the sweater back on, right? That is the day-night cycle due to the fact that the Earth is rotating, right? So the rotation rate can influence the temperature at the surface, where if you rotate faster, you have a more constant average temperature, whereas opposed to you could have more cycles if it's less, right? Okay. All right, let's talk really briefly about the start of the greenhouse effect. I know you all been asking me questions in order to get me to go slower. Okay, so the greenhouse effect happens to you on a day-to-day basis, probably. Can anyone give me an example of a greenhouse they get into quite frequently in the summer? Cars. Cars are little greenhouses. Okay, so a long time ago, they figured out that glass lets light through, but doesn't let infrared light out. So if you want to grow stuff in a place that's cold, you can build a house. You can replace the walls and the roof with glass. And then you can grow all of your nice little vegetables. And the light will come in. The plants will be stoked because it has light. But then even if it's freezing outside, the inside is warm because the infrared light can't escape. Because infrared, the glass that you have in your car is opaque to infrared radiation. It does not transmit infrared radiation. So a snake inside your car can't see you coming. That's what you need to think about. You can see the snake, but it can't see you. I mean, for different reasons, right? That makes sense? Okay, this is the basis of the greenhouse effect. So what we'll be talking about for the next, we'll talk obviously about weather, talk about storms at the beginning of class, but really we'll also be talking about what is the impact of adding more water vapor, what is the impact of adding more CO2, and what is the impact of adding more methane, all of which are really good at grabbing infrared light and trapping it. So these gases act like glass, very close to the surface of the Earth, trapping the light from the sun in and not letting it escape, driving up the temperature, causing more evaporation of the surface, which creates more water vapor, which makes it hotter, which drives up more evaporation, which makes it hotter, and maybe kills us all. Okay. Okay, great.